In this video, we'll cover a little more complex calculation that involves pH, the Ka and the Kb, and equilibrium concentration. So here it says the pH of 0.051 molarity solution of nitrous acid, HNO2, is 2.32. What is its Ka? So let's go ahead and write down what we know so far. So we know that the pH is equal to 2.32. We also can set up the Ka equation, which is hydronium concentration NO2 minus concentration all over the NO2 or HNO2 concentration. The pH, this portion really represents at equilibrium, because you know that the hydronium ion has been formed at equilibrium. Whereas this portion, this is the initial concentration of the HNO2, the initial, okay? So this, all the stuff that you see on the Ka value right here, this area, that's at equilibrium, not initially. So we're going to have to be utilizing ICE tables, solving out for the hydronium ion and so on and so forth. So let's target the H3, the H3O plus, which is the hydronium ion. So pH is equal to the negative log of the hydronium ion. And we know that pH is 2.32 is equal to negative log of the hydronium ion. And we're going to go ahead and press negative. We're going to put the negative on the other side. So we have negative 2.32 is equal to log of the hydronium ion. Now let's take the anti-log of that to get just the concentration of the hydronium ion. So 10 to the negative 2.32. Or you could press second log, which will give you the same setup. And that's 0.00479 molarity. So we now have the concentration of hydronium ion, but we need to find the rest. Well, let's do an ICE table here. Initially, we have the information of the nitrous acid being 0.0516 molarity. There are no products, at least not yet. As time passes, there's a change, or C, that where C represents change, and that change would be minus the X and plus the X for these guys, because that's how much it's been produced, since this is all 1:1:1 ratio. At equilibrium, you're going to add this all up, okay? And that would be 0.0516 plus the minus X, which is just minus X. 0 plus X is just X. 0 plus X is X, okay? We can plug these values in to the Ka, but what do we know about hydronium right here? This one. We already have this X, which is right here, okay? Okay, so Ka, I'm going to rewrite this. Ka, we can see this as X times the X all over 0.0516 minus X. Or we can rewrite this X to the second power 0.0516 minus X. Well, we know that the X is the hydronium ion, which is the same thing as this. So therefore, it is 0.00479 to the second power all over the subtraction of this 2. 0.00479. Let's plug this in. It's 0.00479 to the second power. Enter, and I'm going to divide that by the subtraction of the two numbers, minus 0.00479. That would give me 4.910 times 10 to the negative 4. I don't really like working with negatives, but we'll go ahead and put 4.89 times 10 to the negative 4 is my Ka value. This learning check shows that the pH solution of household ammonia is NH3, a 0.950 molarity solution of ammonia is 11.612. What is the Kb for NH3? So I'm going to set you up a little bit, and then you're going to try this on your own and come back and check this video, see if you got it correctly. So say you have a pH, not pOH, pH of 11.612, and you have a concentration of NH3. This one is going to be your initial. So your Kb should be concentration of NH4 and OH minus all over the concentration of NH3. What is Kb? Okay, what is Kb? Now notice that this is a concentration of OH, and right now you have pH. We want to know the concentration of OH. So can we get POH? Sure. Remember that pH plus POH must equal 14. So if my pH is 11.612, we can find POH. I'm going to subtract 11.612 both sides, and if you do that, you would get 2.39. Approximately 2.39. So let me rewrite this. POH is also known as negative log of the OH minus concentration, and 2.39. So you're going to take an anti-log of this. All right, so I'm going to leave you here and see if you can solve the rest of the problem and come back and check this video for the key. And here is the key.